Good day, teachers. How are you today? Hoping you're doing great and safe.
In today's class, we are going to talk about primes and their distributions.
We will look at some basic concepts of prime and prime factorizations, as well as proving one of the most important theorems in mathematics, the fundamental theorem of arithmetic.
Then we will look at the infinitude of primes and some methods of factoring numbers into their prime factorization.
Kindly give your utmost attention as we discuss to you our topic. So, sit back, relax, and enjoy learning.
Hello everyone, I am Madeleine Rivero, the first reporter of Group 1 with the topic, Primes and their distribution. For better understanding of our topic, let me define few terms. First, let us define divides, divisor, and multiple by saying that A divides B, written A divides B if B divided by A is an integer. Here, A is a divisor of B and B is a multiple of A. We use these terms to help us in defining the terms prime and composite by saying that an integer p greater than 1 is called a prime number or simply a prime if its only positive divisors are 1 and p. An integer greater than 1, which is not a prime, is termed composite. Example of primes among the first 10 integers, 2, 3, 5, 7 are all primes, while 4, 6, 8, 9, 10 are composite numbers. Note that the integer 2 is the only even prime, and according to our definition, the integer 1 plays a special role being neither prime nor composite. Also, the notion of two integers m and n being relatively prime means that the only divisors that m and n both share are 1. This can also be stated by using the greatest common divisor, which is the largest number that divides both m and n, by saying that the greatest common divisor is 1, written as GCD of mn is equal to 1. Now, let's start our discussion with a set of lemmas that we'll be using to prove the fundamental theorem of arithmetic later on. Are you ready? Okay, let's do this. Lemma 1. A prime p is either relatively prime to an integer n or p divides n. Proof: since p is prime, then by definition, the only factors of p are 1 or p. Thus, GCD Pn is equal to 1 or GCD Pn is equal to p. If GCD Pn is equal to 1, they are relatively prime, and if GCD Pn is equal to p, then p divides p and p divides n. So if p is a prime, then p is either relatively prime, n, or p divides n. Let us proceed to lemma 2, which states if p is a prime and p divides ab, then p divides a or p divides b. That is, if a prime divides a times b, then it must divide a or b or both. For example, if we know that 7 divides 462, which is equal to 14 times 33, then it must divide either 14 or 33. So in this case, 7 divides 14, in which 14 is one of the factor of one of the factors of 462. We will not prove this lemma anymore. What is more important is to understand that this lemma only holds when P is a prime number. If P is composite, however, then even though it divides A times B, there is no guarantee that it divides A or B. For example, consider 36, which is equal to 4 times 9. Although 6 divides 36, it does not divide either 4 or 9. Again, if 6 divides 36, 6 does not divide either 4 or 9. Lemma 2 makes claims only about prime numbers that divide products A times B. Note that this argument can be extended to encompass a product of more than just two factors. Here are the two corollary of lemma 2. First corollary states if P is a prime and P divides A sub 1 times A sub 2 times A sub n, then P divides A sub k for some k where k is greater than or equal to 1 but less than or equal to n. Corollary 2 states if P, Q sub 1, Q sub 2, Q sub n are all primes and P divides Q sub 1 times Q sub 2 times Q sub n, then P is equal to Q sub k for some k where k is greater than or equal to 1 but less than or equal to n. Next is lemma 3. If n is the product of prime factors and if P prime and we have P divides n, then P is one of the prime factors of n. The proof: let n is equal to Q sub 1 times Q sub 2 times Q sub n be a product of prime numbers and P divides n, then by lemma 2, we know that P divides Q sub I for one of the Q sub i's. So if P divides Q sub I and both are prime, then P is equal to Q sub I. That's the end of the proof. Next, let us proceed to lemma 4. Lemma 4 states that every number n greater than 1 can be written as a product of prime divisors. We will not prove this lemma here, but you can try doing it later. This lemma can be proved using strong induction or what we knew principle of mathematical induction too. Okay, now, after looking at some of the simpler properties of prime numbers, we are ready to learn at the most important theorem about prime factorization, the fundamental theorem of arithmetic. Fundamental theorem of arithmetic states that every positive integer n greater than 1 can be expressed as a product of primes. This representation is unique apart from the order in which the factors occur. To prove this theorem, we use lemma 4, which shows us that every n greater than 1 can be factored into primes. All that is left is to show that uniqueness of this factorization. Okay, let us suppose that there exist two factorizations for n, which is equal to P sub 1 times P sub 2 times P sub r equal to Q sub 1 times Q sub 2 times Q sub p. Since each P sub I divides n, which is equal to Q sub 1 times Q sub 2 times Q sub p, then by lemma 3, we know that each P sub I is equal to Q sub I for some j. Conversely, we see that each Q is equal to some p as well. This shows that each factorization of n contains the same prime numbers. The only difference may be if one prime occurs more times in one factorization than in the other. If this is the case, however, and A occurs more times in the P factorization than in the Q factorization, we can simply cancel A repeatedly until we have one or more A's on the P side and none left on the Q side. This would contradict lemma 3, and thus each prime appears the same number of times in each factorization. Therefore, we have shown that every integer n greater than 1 has a unique prime factorization. End of the proof. Okay, this idea of unique prime factorization as well as the 4 lemmas that we have discussed a while ago, which we use to prove this theorem, can be found in Euclid's Elements in books 7 and 9 from Orion 1948. We are done with a discussion about fundamental theorem of arithmetic. I hope you have learned something from my discussion. It would be a great help in understanding the topic that will follow. Moving on to our next topic, we have Ma'am Annalor Lucera. Ma'am?
Thank you so much, Ma'am Madeleine, for that very informative and interesting presentation. I hope that you're still with us because at this juncture, I am going to tackle the prime decomposition of n.
Several of the primes which appear in the factorization of a given positive integer may be repeated. For example, 360 is equal to 2 times 2 times 2 times 3 times 3 times 5. By collecting like primes and replacing them by a single factor, we could rephrase the fundamental theorem of arithmetic, or FTA, as prime decomposition of n as its corollary. Now, what is prime decomposition of n? So let us define first what is prime. As what I've mentioned a while ago by my groupmate, prime is a whole number greater than 1 whose factors are 1 and itself. Decomposition means a breakdown of numbers into parts. And in here refers to a natural number. Therefore, prime decomposition of n means breaking down a number into prime factors. Corollary of FTA says any positive integer n greater than 1 can be written uniquely in a canonical form. N is equal to p sub 1 raised to the power of k sub 1 times p sub 2 raised to the power of k sub 2 to p sub r raised to the power of k sub r, where for I is equal to 1, 2, to r. Each k is a positive integer and each p sub I is a prime, with p sub 1 less than p sub 2 less than 2 less than p sub r. To illustrate the canonical form of the integer 360 is 360 is equal to 2 raised to the power of 3 times 3 raised to the power of 2 times 5. Example number 1. Determine the prime power decomposition of 273. Our first prime, 2, does not divide 273. However, 3 divides 273. Thus, we obtain 273 is equal to 3 times 91. 91 is no longer divisible by 3 and is also not divisible by 4, 5, or 6. 7 divides 91 though. Hence, we obtain 273 is equal to 3 times 7 times 13. Note that 3, 7, and 13 are all primes. So, we are done. Hence, the prime power decomposition of 273 is equal to 3 times 7 times 13, where P sub 1 is equal to 3, P sub 2 is equal to 7, P sub 3 is equal to 13, and K sub 1, K sub 2, and K sub 3 is equal to 1. Example number 2. Determine the prime power decomposition of 1008. First, notice that 2 divides 1008. Hence, 1008 is equal to 2 times 504. It should be rather clear that 2 divides 504 as well. Hence, 1008 is equal to 2 times 2 times 252. Again, 2 divides 252. Hence, we obtain 1008 is equal to 2 times 2 times 2 times 126. 2 divides 126. So we obtain 1008 is equal to 2 times 2 times 2 times 2 times 63. 2 does not divide 63, but 3 divides 63. So we obtain 1008 is equal to 2 times 2 times 2 times 2 times 3 times 21. 3 divides 21. We obtain 1008 is equal to 2 times 2 times 2 times 2 times 3 times 3 times 7. 7 is prime, so we are done. Hence, the prime power decomposition for 1008 is equal to 2 raised to the power of 4 times 3 raised to the power of 2 times 7, where P sub 1 is equal to 2, P sub 2 is equal to 3, P sub 3 is equal to 7, and P sub 1 is equal to 4, P sub 2 is equal to 2, and P sub 3 is equal to 1. Thank you so much for listening, and I am hoping that it's clear for all of you. Again, my name is Ana Lulicera, and I am the second reporter of the group. Now, let us proceed to the infinity of primes to be discussed by the third reporter of our group. Thank you so much.
Good afternoon, everyone. Are you still there? Great. By the way, I am Jeremy Uyanguren. At this moment, we are going to discuss the infinity of primes by Euclid of Alexandria. Okay, let's start. It is difficult to determine directly from the definition whether there are many primes, indeed, whether there are infinitely many. To understand fully the infinity of primes, let me introduce to you the person behind its proponent. Euclid of Alexandria, a Greek mathematician who lived in several centuries before the Common Era. Aside from his many contributions to geometry, he also made important contributions to our understanding of numbers. In particular, Euclid showed that for any finite number n, there are more than n prime numbers. This is equivalent to what we would say, given any finite list of prime numbers, one can always find a prime not on the list. Hence, the number of primes in infinite. Theorem. Let us discuss some theorem. There are an infinite number of primes. Proof. Euclid's proof is by contradiction. Let P sub 1 is equal to 2, P sub 2 is equal to 3, and P sub 3 is equal to 5, P sub 4 is equal to 7. Be the primes in ascending order, and suppose that there is a last prime, we call it P sub n. Now consider the positive integer. P is equal to P sub 1, P sub 2, to P sub n plus 1. Since P greater than 1, when we put fundamental theorem of arithmetic 58 to work once again and conclude that p is divisible by some prime p, but p sub 1, p sub 2 to p sub n are the only prime numbers, so that p must be equal to 1 of p sub 1, p sub 2 to p sub n. Combining the relation, p divides p sub 1, p sub 2 to p sub n. With p divides p, we arrive at p divides p minus p divides p sub 1, p sub 2 to p sub n, or equivalently, p divides to 1. The only positive divisor of the integer is 1. Is 1 itself, and since p greater than 1, a contradiction arises. Thus, no finite list of primes is complete, whence the number of primes is infinite. That's the end of my discussion. We have proved that the number of primes is infinite, so it is not possible to find all prime numbers. However, suppose we wanted to find all prime numbers up to a certain number. How are we going to do that? Do you have any idea? Our next reporter will answer that for us. So let's have Mom Princess. Mom?
Thank you, Mom Jera. I'm really hoping I could give you the answer you wanted to hear. Anyway, how are you there, teachers? Do you also have an answer question there? Kidding here. Okay, back to the topic. Of course, Mom Jera is right. It is not possible to find all prime numbers since we have already seen that there are an infinite number of them. However, suppose we wanted to find all prime numbers up to a certain number. What would be a good way to go about doing that? For any number, for any given natural number, of course, we could just attempt to divide it by a smaller natural numbers. For example, if we wanted to know whether 43 was a prime or composite, we could try dividing it by 2, then by 3, then by 4, then by 5, and so on, until we will eventually reach 42 and realize that 43 is indeed not divisible by any numbers aside from 1 and 43 itself, making it a prime. And that is why we need what we call the sieve of Eratosthenes method. What kind of method is this? Who is the person behind this method? Do you have any idea who is he? Yes, you got it right. He is Eratosthenes of Cyrene, the ancient Greek mathematician, a poet, and scientist. Eratosthenes of Cyrene suggested a relatively efficient method of determining all the prime numbers up to a certain number. He was the director in the famous Library of Alexandria and was gifted in all branches of learning. He was nicknamed Beta because it was said he stood at least the second in every field. And the third one, the accurate measurement of the Earth's circumstances by a simple application of Euclidean geometry. A method that he introduced is the sieve of Eratosthenes. It is an algorithm used for finding all the prime given an integer n. The scheme calls of writing down the integers from 2 to n in their natural order, then systematically eliminating all the composite number by striking out all multiples of 2p, 3p, 4p, and 5p. Of the primes, p is less than or equal to the square root of a. The integers that are left on the list, those that do not fall through the sieves, are primes. Here is an illustration of his method. Consider how we might find all the prime numbers up to 100. First is to write down all the integers from 1 to 100, where 100 is the largest integer. Then you start with 2, since by definition, 2 is neither prime nor composite, remember? The next one is to circle 2 and cross out every integer that is multiple of 2. When we say multiple of 2, any number that could be divided by 2, as you can see, we just eliminated and cross out numbers that are multiple of 2. Then the next step is to look for the next number that is greater than 2 and that has not been crossed out, and that number is 3. Then circle number 3 and cross out every integer that is a multiple of 3. Then return to the beginning and start. The first integer greater than 3, the first integer that are then return to the beginning and start. The first integer greater than 3 that are not crossed out, namely 5. Circle number 5 and cross out any integer that are not crossed out and are multiples of 5. To find the multiple of 5, look for the numbers that ends with 0 and 5. Then just continue this process and look for the next number that is greater than 5 and has not been crossed out. That number is 7. Circle number 7 and cross out every integer that is multiple of 7. Since the greatest integer that are greater than 7 but less or equal to the square root of n are all crossed out, therefore the process ends. Then to find the primes of n when n is then to find the primes of n when n is equal to 100 is to encircle all the prime numbers left and cross. Then the encircled numbers are called prime. And the positive integer which remain to the width are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97 are all prime less than 100. Did you understand the method? Very well. Thank you for staying with us in this joyful learning moment. We are looking forward to still have you all in the next topic that we'll discuss by Sir Aiken S. Rakasa. Sir?
Good day once again, my beloved professor and educators, and soon to be master teachers, if and only if we could pass this subject. Now, let's move on to the next chapter of our learning for this session. I hope you are still listening, and remember, always keep your mind alive and alert. We are almost done with our discussion. Okay, let's do this. Oh, I forgot to introduce my name. By the way, I am Aiken S. Ragaza, one of the members of Group 1. I am tasked to discuss Euler's method of factorization. This is the last topic that we're going to discuss today. Just like the other method, this method has also a proponent or a person who is behind this method. The person behind this method is Leonhard Euler. He was an amazing scientist whose contributions are evident on nearly every branch of mathematics. The sheer volume of work that he did in his lifetime is unreal. It has been said that his entire collected works would fill the pages of over 100 large books. He was born in Switzerland in 1707. He held positions at the Academy of St. Petersburg as well as the Academy of Berlin. He first mentions factorization of a number using the sum of two squares in a letter on February 16, 1745 to Christian Goldbach, a German mathematician. This is what we are interested in here or in my discussion. So Euler's factorization method only applies to numbers which can be represented in at least two different ways as the sum of two perfect squares. So n is equal to a squared plus b squared. So now let us begin by assuming that n is odd parity. So one of the numbers is odd and the other is even. So without loss of generality, we can say that A is odd and B is even. The next step in Euler's factorization is to look at the second way to represent n as the sum of two squares. N is equal to c squared plus d squared. Kanina, n is equal to a squared plus b squared. Ngayon naman, maghahanap tayo ng ibang values na ma-represent natin si n. Then, c squared plus d squared is also equal to a squared plus b squared. Where again, we have c is odd and d is even. So for example, a number 221. So kung ato ang i-try, mangita tag number nga kung isam na to sila, duha ka number nga perfect square nga duha ka number nga kung ato silang isam, ang ilang equivalent is equal to 221. So pwede imuon na to siya nga 11 squared plus 10 squared. Okay? So pwede po nato siya nga i-represent as 5 squared plus 14 squared. So kung ato ang i-check, 11 squared plus 10 squared, this is equal to 221. And then 5 squared plus 14 squared, equal lang gyapon na siya sa 221. And then our A and C, tama. A and C natin dito is odd. Odd yan palagi, according to our definition. Okay? To show that the two representations of n is equal to a squared plus b squared is equal to c squared plus d squared leads us to a factorization of n. We look at a squared plus b squared is equal to c squared plus d squared. This implies that a squared minus c squared is equal to d squared minus b squared. And also this implies that quantity a minus c times a plus c, or quantity a plus c. This is equal to the quantity d minus b and multiplied to quantity d plus b. Okay? I want you to remember this equation that I will introduce to you, or the derivation of our formulas, so that magamit nato siya sa pag-solve nato karon sa K, L, M, and R. So gamito nato ning proof ni Euler, yung definition, to solve our K, L, M, and R. Then we will substitute it to the formula of n. Okay? Para makuha yun nato ang factors. Duha ka factor. Okay, so now let K is equal to GCD of A minus C, comma, D minus B. So note that K is even since A minus C and D minus B are both even. So we have A minus C is equal to KL. Paki-take note ninyo kay magamit na to nga formula unya. And D minus B is equal to KM. With the GCD of L and M is equal to 1. Substituting this, we get KL, the quantity of A plus C, is equal to Km times, or the quantity D plus B, implies L times the quantity A plus C, is equal to M, ambot lang kung tama ba niya akong pagbasa, is equal to M, pwede po siguro, is equal to M, open parenthesis, D plus D, or close and close parenthesis. Basta makita ninyo na M, pwede na po dito M times D plus B. Okay? So, since L and M are relatively prime, so maingon na to nga relatively prime man si L ug M, kay ang iyang greatest common denominator kay equal to 1. So, makaingon lang ta nga relatively prime siya kung iyang GCD kay equal to 1. Then M must divide A plus C, which gives A plus C is equal to MR. This implies LMR is equal to M times D plus B. Implies LR is equal to D plus B. So we have A plus C is equal to MR. Magamit na po natin ang mga formula unya, and D plus B is equal to LR. But the GCD of L and M is equal to 1. So this means that R is equal to the GCD of A plus C and D plus B. Okay? And thus is also even. So the factorization that we are looking for is N is equal to open parenthesis K over 2 raised to 2 plus R over 2 raised to 2 close parenthesis multiplied by M squared plus L squared. Makita ninyo diha kana nga formula, magamit na to na unya para pag-solve sa duha ka factors. Okay? So now, kaning formula, dili lang ni diri kutob, atuan siyang gamiton para makuha nato ang duha ka factors. So we see that this factorization is in fact a valid one. Now let us do an example by factoring the number n is equal to 2,501. It is apparent that 2,501 is equal to 50 squared plus 1 squared. And after some minor calculations, we can see that 2,501 is equal to 49 squared plus 10 squared as well. So now, we can let A is equal to 1, B is equal to 50, and C is equal to 49, and D is equal to 10. Timan-an ninyo na kinahanglan ang ato ang A ug C is add. So pwede na to sila balihon ang duha ka values. Balihon na to sila para makakuha ta nga ang atong A mahimo siya nga add. Okay? So karon nakuha na nato ang values ni A, B, C, and D. Then, A minus C is equal to negative 48. A plus C is equal to 50. D minus B is equal to negative 40. And D plus B is equal to 60. So this leads to K is equal to 8. L is equal to 6. M is equal to 5. And R is equal to 10. So if you were asking if kung paano nakuha ni Euler yung values ng K, L, M, and R, dimension na nako ganina na kinahanglan ninyo nga timan-an tong mga equation. See for example, kung paunsa nakuha ang value ng 8, so here, so ano nga yung value ng K? So kanina, sinabi ko na, and then, in-explain na dito sa proof and definition ni Euler. Now, let K is equal to the GCD of A minus C and D minus B. So, ano yung values ng A minus C? A minus C is equal to negative 48. And then we have D minus B is equal to negative 40. So, kung kwaon na to ang ilang GCD, ang GCD sa negative 48 and negative 40 kay 8. Okay? And then, we know that K is equal to the GCD of A minus C and D minus B. Therefore, our K is equal to 8. So, the same process lang sa pagkuha sa L, M, and R. Gamiton lang ninyo itong mga equation nga naa sa taas, nga ako ang na-mention na ganina sa previous slide. Then, mo-arrive ka sa answer na ang L is equal to 6, M is equal to 5, and R is equal to 10. Now, gamito na po nato itong pinakalas nga formula kung paunsa makuha ang factors, then mag-given naman ang n, so gamito lang nato ito siya nga formula. So again, the formula, the factorization that we are looking for is, so atuan na ni siya nga na prove nga tinuod ni siya nga formula. So ang formula is n is equal to k squared over k over 2 raised to squared plus r over 2 raised to 2 or to the power of 2 times m squared plus l squared. So kung imuha na siyang i-substitute ang mga values ni k, l, m, r, and n, so i-substitute na to sa ato nga formula kato nga mga values, we will arrive at 41 times 61. So therefore, ang atuang values nga gipangita kay 41 o 61. So again, naani siya kaning relationship sa pagkuha pod sa factorization using the Fermat's. So si Fermat na po ilaing pamaagi kung paunsa makuha ang factorization. And then kang Fermat manggod kay kung kang Euler is sum of two squares, kang Fermat pod kay difference of two squares. So related lang na sila dito, lahi ang pamaagi ni Fermat, pero ang Fermat dili na nato na i-discuss diri sa ato nga session karon. It is not wala na siya na appeal sa amo nga topic nga i-discuss karon. But however, kung gusto ninyo nga mangita og laing pamaagi para makuha ang factors, pwede pod nato magamit si Fermat. Labi na kung makita ninyo nga ang number, pwede nato siya i-represent as difference of two squares. But kung makita nato nga pwede nato siya i-represent sa the sum of two squares, pwede po nato gamiton ning kang Euler. So medyo dali lang ning kang Euler. Kung ako ang nakita dito kang Fermat, medyo lisod-lisod siya pero masabtan ra gihapon. Okay? This is the end of our lesson. I hope you have learned something from us as we tried our best to understand our topic so that we could share learning that could help us understand this subject. We are looking forward for more collaboration to all of you in the quest of learning.
This has been Icon S. Rakasa.
Princess J.D. Ondalok.
Jeremy B. Uyangren.
Ana Lucy Licera.
Madeleine Rivero, your reporters of the day. Thank you and God bless.